Yeah. Well, thank you very much, Barney, for inviting me. This has been a lot of fun. And thank you for agreeing to pronounce Blumenthal the awful American way. But you know what? That's me. That's who I am. So I appreciate the truth, the fidelity. Yeah. So today I'm going to be talking about some work of mine, joint with these fine people, Jinqin Xue, Yuan Yang, and Lai-Sang Young, having to do with random perturbations of predominantly hyperbolic systems, a term that I will get to explaining momentarily. So just to orient ourselves, I'd like to briefly recall what hyperbolicity is, right? This is our favorite Onedimorphism, the cat map, right? 2, 1, 1, 1, right? And all it's doing is it's taking the cat and horribly mutilating it with successive iterates, right? And so you have expansion along the expanding eigendirection of the 2, 1, 1, 1, right? And contraction perpendicular to it. It's a symmetric matrix. And here I picked out a few iterates of the Smale solenoid, right, which is doing kind of a similar thing, but this is a volume compressing map, right? So it's taking the donut, and you can think it's you stretch it out, right, in such a way that you're actually contracting the volume of the donut, and then you ravel it back up and stick it inside, right? And you do this a few more times, and you iterate infinitely many times, and you get this zero volume attractor, okay, that has this kind of characteristic strange attractor geometry. But the essential thing, and the thing that I want to really focus on, is that there's expansion along the theta direction, right, and contraction along these cross sections, okay? And this is kind of the characteristic dynamical demeanor of these uniformly hyperbolic systems. And so the theory of uniformly hyperbolic systems was pioneered in the 70s, 60s and 70s. Anosov, Sinai, Ruel, Bowen, lots of people. I don't want to get too far into it, except to say that the theory is quite classical at this point. But I'm not going to talk about that today. I'm going to talk about what happens when the expansion and contraction in the dynamics is not uniformly realized in phase space, okay? And so the kind of maps that I'm interested in are those which are hyperbolic on the manifold, right? The infinitesimal stretching and contracting in phase space. They're hyperbolic on that manifold, except for the dynamics on a small set, whatever the heck that means. But if you'd like maybe a small volume set, okay? So maybe there are some natural scaling parameters in my map, and then this is small with respect to those, right? And so the kind of question is, what is the asymptotic dynamical regime? What can I say about it? Does the hyperbolicity win in the end? Okay, and so to really get an appreciation for why this is an interesting and subtle and very difficult question, yes.
C is not necessarily invariant.
Exactly. So in this game, C is strictly non-invariant. C is going around all over the place. Okay, so I'll get a little more precise. So I have in mind these examples where the set C actively harms or reverses the hyperbolicity. Okay, and so this is already. It's already almost trivially easy to come up with the one-dimensional example of the quadratic family on the unit interval, okay? On the symmetric interval -1, 1. And so away from 0, well, it's the derivative, it's just 2x, right? So away from an extremely tiny neighborhood of 0, right? You're having expansion, right? It's expanding to order, expanding by a factor of at least like 1.5, except for a small neighborhood of 0, right? But at 0, that derivative growth is harmed, okay? And so if trajectories venture too close to 0, that accumulated derivative growth reverses, okay? And can actually become contractive. All right, and then, well, okay, but this is kind of a distinctively one-dimensional issue, and really what I'm more interested in are two or higher dimensional examples. And so what I'm going to talk about predominantly today are models that exhibit this kind of cone twisting, right? So in these uniformly hyperbolic examples, in these uniformly hyperbolic examples, there was a cone in tangent, a cone of vectors that got mapped into itself, okay, and all directions in that cone were strongly expanded, all right. Whereas as we'll see with this example with the standard map family, is that that good cone of expansion gets kind of twisted in a bad way, gets kind of twisted in a bad direction, all right? And so in both of these cases, okay, checking whether the hyperbolicity wins out, all right, that is whether you get a positive Lyapunov exponent asymptotically, is this incredibly subtle cancellation problem. Okay, do the phases of expansion overcome the phases of contraction in the system, right? And so, of course, this story for the quadratic family has been extremely well studied at this point, and we can say actually that for almost every parameter C, you have either a positive Lyapunov exponent or sinks, okay, and that there's a positive Lyapunov exponent for a positive Lebesgue measure set of points, right? But unfortunately, that positive Lebesgue measure set of points is hopelessly intermingled with the set of points for which you have a sink. So which parameters correspond to which regime is just impossible to check. They're hopelessly commingled with each other, right? And the situation is somehow even worse for the standard map family. It's an open problem to check that the standard map has a positive Lyapunov exponent on a positive volume set. That is to say that the hyperbolicity wins out for the asymptotic dynamics. This is an open question. To the best of my knowledge, this is still an open question. Correct me if I'm wrong. Not for lack of trying, though. Of course, Tom. So,
Can I ask, I
yes.
think positive Lyapunov exponent means hyperbolicity wins.
Yes. I mean, but I'm specifically interested in a positive Lyapunov exponent on a positive Lebesgue measure set of initial conditions. So at a point, I can define this quantity. If I just look at the linearization at a point and I look at the asymptotic growth rate of the norm of the derivative, right? My question is whether I have positivity of this exponent for a positive measure set of points. It's a different question to ask whether there exist points for which you have a positive exponent, right? But from the viewpoint of I'm taking the perspective that in simulations you only ever see Lebesgue typical trajectories, right? And so if I only have positivity of the exponent on a zero measure set, that didn't really tell me about Lebesgue typical trajectories, right? So that's what I'm regarding as hyperbolicity in this context. Okay? Okay. So the subject of this talk is to take this problem in deterministic dynamics and try to find something tractable that we can do, okay? And what we can do, and what I'll talk about today, is to obtain positive Lyapunov exponents when I add small IID random perturbations to my dynamics, okay? With the idea being, and hopefully as the talk progresses, this will be kind of made a little more clear, that the introduction of noise kind of shakes loose the hyperbolicity in the system. It becomes this less subtle cancellation problem, and actually things become considerably, astronomically easier, I should say. So what I'll talk about today are results on the Chirikov standard map, and also these also a class of volume contracting systems, right? With a not really Henon, but with a Henon flavor, right? With a seasoning of Henon somehow. And I'll also talk a little bit about some recent work on one-dimensional dynamics as well that actually hasn't seen yet. So. So this is kind of the plan, and I will dwell mostly on the standard map because I think we're a volume-preserving crowd here, so that might be more interesting to you all. Okay. So 2D dynamics. So I want to talk about this cone twisting business. So this is a version of this is one parameterization of the standard map. Okay, when b, this parameter b, I like to keep this parameter here because the discussion here doesn't really matter whether I preserve volume or not. So you can think of b as 1 if you like, but b I could take to be a half, for example, and this is fine. But this parameter L is stupidly big, right? Think like a Google, okay? G-O-O-G-O-L. So what I mean by an invariant cone is that away from the zeros of the derivative of this term, that is, away from these grayed out strips that pass through the domain of the torus where this map is acting, that this cone is mapped strictly into itself. And these vectors are expanded. Okay. So actually, I would like just to write down, just to fix some ideas, I'd like to write down the linearization of this map. So F is Cherenkov standard map. And the linearization what's a factor of 2 pi between friends? Okay? I'll just keep that up there for the rest of the talk. So when cosine is 0, or when cosine is really small, that top left coordinate is small, right? It's on the order of a constant order 2. But actually, you know what? I'm going to be even sloppier. Forget the 2. Forget the 2 even. For what I'm going to say, the 2 doesn't matter. So when away from the zeros of cosine, right, that top left coordinate is huge, and so I get huge expansion in the horizontal component, right? But near the zeros of cosine, this that is this small shaded region, this kind of order L inverse neighborhood, okay, of these points where cosine is 0, that is going to be my critical set, where hyperbolicity is not true. Okay. In fact, the dynamics is rotational. This looks like a rotation by 90 degrees, practically speaking. It might as well be. And so this really sucks, because when trajectories enter that critical strip and they see the rotation, my previously expanding direction got rotated practically 90 degrees, could have been, right, rotated into my into a vertical direction. Okay. And in the vertical direction, I can see contraction. I can see contraction of order L, okay? And so estimating Lyapunov exponents for iterates of this thing becomes this incredibly delicate cancellation problem, okay? And this issue of twisting cone fields and so on is absolutely real, okay, and is made manifest by the presence of elliptic islands for these systems. So actually in the mid-90s, Duarte proved a set of results about the proliferation of elliptic islands for a variety of volume-preserving diffeomorphisms. And for the Cherenkov standard map, what he shows is that for a residual set of sufficiently large L, that elliptic islands are dense, okay, are dense in phase space. While, okay, let's kind of ignore the dissipative setting. But in the dissipative setting, it also sucks. Right. This is also extremely difficult in the dissipative setting. For this model, when b is strictly less than 1. And so, kind of the best results I can tell you, right, are.
Sorry, can you speak again what an elliptic island is?
Oh, I'm sorry. Let's be a little sloppy and say that an elliptic island is actually an elliptic fixed point, or an elliptic periodic point. Okay, but island is supposed to evoke this kind of local KAM picture. Okay. What happens when you have an elliptic periodic point, and please correct me if I screw this up, but what happens if you have an elliptic periodic point is you can zoom in a lot, and then when you zoom in enough, you get a kind of KAM picture, and you see a ton of tori in the vicinity of that periodic point, right? And so actually, elliptic periodic points aren't naked in the phase space. They're ensconced in these tori, right? And so actually, you don't see a basin. You don't see like an actual sink, right? But you see this this chunk of dynamics that kind of sits around and like swirls around in the neighborhood of the elliptic fixed point. So that's why I call it an elliptic island, is to evoke that picture. Elliptic islands in a stochastic sea, right? And the stochastic sea is supposed to be the set where the exponents are positive, right? So right, elliptic islands are bad for hyperbolicity, because it's rotational dynamics, right? And if my trajectory enters the vicinity of an elliptic island and stays there for a little while and then comes back out, I have no idea what direction tangent vectors are pointed in, right? They might as well be pointed in the worst direction, after which I'm screwed. I have no control anymore, right? And what I just said, right? Elliptic islands are dense for a residual set of large L, okay? It is possible, it is conceivable that I can tune my L to get rid of all elliptic islands, but I think that's open. That's open, right, Tom?
It's open.
Yeah, yeah.
It could even be true that there's a positive measure set of line. I mean,
Yeah.
of L's. I expect it is actually, but no.
Yeah, yeah. So really, it's a mess. You should anticipate that these elliptic islands are playing a role, right? Yeah. OK, so on the one hand, elliptic islands are everywhere, right? But on the other hand, Gorodetsky proved in 2012 that the top exponent is positive on a set of Hausdorff dimension 2, that for a residual set of L is also relatively dense in phase space. So that's insane, right? This is an intense commingling of completely opposite dynamical regimes in phase space, OK? All right. I have a residual set of parameter of L for which elliptic islands are dense, but the set with the hyperbolic set, the set with a positive Lyapunov exponent, is also relatively dense. Okay. If you're not driven insane by this, then I don't know. Okay. This is crazy. This is very crazy making. I should mention though this very curious and very interesting result of Berger and Tureyev. I would be remiss if I didn't mention it. That says that you can, if you approximate the standard map by very carefully cooked CR perturbations, that you can actually get a positive Lyapunov exponent on those CR perturbations. But that's kind of a tricky thing, and it doesn't shed insight on the core problem, which is cone twisting, to my mind. Oh, R is whatever. I think R can be 2, 3, 5, bigger than 2. The thing is, it's bigger than 2, though. It's not a C1 perturbation.
So there are. So you're saying I can perturb the standard map by a CR perturbation?
Yes, an arbitrarily small CR perturbation.
And I preserve area and everything?
Yes, I preserve area, but I'm not twist anymore.
And can you get coexistence of elliptic islands with that?
I don't know what the CR perturbation looks like, so I can't really tell you what's happening in the CR. But I was told by Simeon Philip earlier today over lunch that the CR perturbed map, actually you have a uniformly hyperbolic positive Lyapunov exponent there, which is kind of funny, right? You don't
uniformly hyperbolic?
Yeah, on a positive Lebesgue measure set, which is kind of peculiar. It doesn't address what.
So you're saying it's uniformly hyperbolic on some.
This is weird.
Strange, yeah.
It's a little strange. It doesn't see, and you're really cooking this CR perturbation, right?
Yeah,
It's interesting.
It is.
It's very interesting. Yeah. So this is Berger Tureyev, released this year, I think. So. I should say that kind of that in the dissipative setting, when instead of 1 you have a B here, you can still ask questions like, does there exist a strange attractor? Do I have a positive Lyapunov exponent? And so on. Lebesgue is no longer invariant. This is volume contracting when B is less than 1. But so kind of the best known results for models of this kind, not exactly for this model, but for models of this kind, are for the Hannon map, when that parameter B is perturbatively small. So you think of these results, Benedictson and Carlson, and later work by Don Wang and Lai-Sang Young. You think of these results as perturbations of one-dimensional dynamics. The one-dimensional dynamics that happens to be very well understood, but the 2D dynamics, which is considerably harder. Even still, that perturbation into the second into the second dimension is really difficult to deal with. These three papers I've listed are easily 400 pages of mathematics, kind of getting to the brink of what a human can reasonably understand. So it's hard. It's really hard. Okay. So, but that's not what I'm here to talk to you about. What I'm here to talk to you about is how the introduction of small, independent, identically distributed random perturbations to the dynamics actually makes the problem of determining positivity of Lyapunov exponents astronomically, exponentially easier. Okay, I take a logarithm of 100 and I get 10, and that's about the order of magnitude of the length of the papers that you need to prove these results. It's quite nice. I don't want to talk about this. What I do want to say, though, and in contrast with the deterministic setting, is that even in settings where you can determine a chaotic asymptotic regime, for say Henon or for maps kind of like Henon, even when you can determine an asymptotic regime for say a parameter, right, or for a positive Lebesgue measure set of parameters, right, you still had to do this kind of infinitary parameter exclusion. You had to exclude some B's and some L's along the way, right? And you anticipate that the kind of conditions you develop on the B's and the L's are fundamentally uncheckable, okay? Because it is known, true fact, that if you perturb systems with these genuinely non-uniformly hyperbolic chaotic regimes, you should anticipate totally breaking the hyperbolicity, right? So you'll never know which parameters correspond to a chaotic asymptotic regime, okay? You'll never know which. You might be able to prove they exist, but you'll never know which ones they are. Contrast that, though, with the picture for systems with randomness, okay? I claim that you can find the parameters in principle, all right? It might be hard, but with a computer the size of the moon, you could probably do it, all right? In the sense that if I fix a noise that I'm applying to a one-parameter family of systems, that it should be a computable problem to estimate this Lyapunov exponent, okay, on a positive Lebesgue measure set.
That exponent's positive. The question is what the sign is.
For volume preserving, yes.
No, but
Yeah, that's right. But the question is what it is, yeah. So yeah, Tom is getting at something. You're a little ahead of me, but yeah, I'll get there. Okay. And then adding noise is not a great sin. That's the last point I want to make about this, is that from the perspective of modeling, if dynamics is supposed to be the study of time iterations of physical systems, right? The sin of adding noise is not that bad, okay? The real world is inherently noisy. When I talk to applied people about these things, they say, yeah, of course there's noise, right? There's noise in the real world. And so adding noise to the dynamics is not so bad. We should be doing this. This is something we should be actively pursuing, I think. So let me get a little bit more mathematical, because I've been extremely amathematical so far. Right? So what I'm doing is the following thing. Start with the standard map. Take b equals 1, b less than 1, whatever you want. But fix the L and the b. And consider an IID, independent uniformly distributed sequence of random variables, uniformly distributed in some epsilon pillbox. Okay? And at every time step, I'm going to perturb the map I apply, okay, to this new guy, which I write f omega I. And all I'm doing is I'm kicking the x direction by that little random guy, my little omega. And so I'm interested in the asymptotic dynamics of these random compositions, okay, where the kick, the omega that I apply at every time step is a different omega, is an independently chosen omega, okay? So this is the noise, right? This is the noise in the system, okay? So when I totally blast this system with noise, or as Tom Spencer observed, not only does this limit exist with probability 1, but you actually expect it to be constant over the x with probability 1. That's not so hard. That's actually not even so interesting. If you don't know how to do it, I can tell you after, fine. But these numbers should exist for all epsilon, okay? And for what I didn't write here is the fact that for any epsilon, the number lambda 1 is positive for the standard map, okay? That's true from Furstenberg's criterion, or a version of Furstenberg's criterion. That's actually not so hard to do. What's far more interesting, though, than just Furstenberg's criterion, which is this very soft thing, which just says there's a positive Lyapunov exponent. What's actually more interesting is to determine whether lambda 1 is on the order of log L, whether lambda 1 is actually experiencing all of the hyperbolicity that the standard map has to offer, right, on the order of log L. So for epsilon on the order of like a half, right, if I just pump this system with a ton of noise, right, and totally obliterate the dynamics, it's an exercise you can safely give to a graduate student to prove that the top Lyapunov exponent is on the order of log L. If I absolutely obliterate the dynamics with noise, right? So if you think about it, right, it's like taking compositions of matrices like this, where this X is chosen IID, okay? It's an exercise you can give to your grad students. I did it. You can probably, your grad students can probably do it if I can do it. So really what's more interesting, right, and the right way to phrase this problem is to determine how small to take the noise, to shake loose the hyperbolicity in the system, okay? If you believe me that the Lyapunov exponent depends continuously on the epsilon, okay, at what threshold do I begin to see really crazy fluctuations in the value of lambda 1 epsilon, right? So that's the right way to at least frame this problem. How much noise do I need to shake loose the hyperbolicity in the system? Feel free to interrupt me and ask questions, by the way. I feel like I'm marching. I'm going very fast. Okay. So our result, joint with Jinxin Xue and Lai-Seng Yang, is to prove that for large L naught, don't worry about this C. The C is like a tenth. For large L naught, and for epsilon exponentially small in L, the Lyapunov exponent exists as constant almost surely and sees as much of log L as I want it to. So I can actually take this 9/10 to be as close to 1 as I want. Okay. That's sharp, obviously. The norms of these matrices are bounded from above by order log L, right? So I shouldn't see a Lyapunov exponent any larger than log L, right? So what this is saying is that actually that hyperbolicity is all realized, okay? So let me explain why this was surprising, or why people thought it was, why I thought it was surprising, actually, is that I made no detailed assumptions about the dynamics of the standard map. This result holds for all L sufficiently large, including those for which F has a big fat elliptic fixed point. Okay? So if F has an elliptic fixed point, I just told you this kind of elliptic island story, right? So the deterministic dynamics has a big fat elliptic island just sitting there swirling around, okay? And because the noise is so small, the dynamics of the random map resembles very closely the dynamics of the deterministic map for extremely long timescales. So how long would it take for if I just started right on top of that elliptic island, right on top of that elliptic fixed point, how long would it take for the randomness to really kick me out of that elliptic island? It would take a damn long time. It would take exponentially long in L, okay? And I just told you to think of L as like 1,000. It takes a trillion years, right? Is it no, it's a googol, yeah. It takes a googol years to get out of the elliptic island. That's crazy, right? How the heck does the randomness win out, right? This is hopefully something that I'll explain today. And so what I just said is a picture that holds for, okay, for all L and for all noise amplitudes epsilon big enough, like this, exponentially small in L, but big enough. If I do a little bit of parameter exclusion on the L, so Tom, this is something you eat for breakfast, right? By doing a tiny bit of parameter exclusion on the parameter L, precluding elliptic periodic points of period less than 3 should do it, okay? You can allow an even smaller random perturbation, okay? But the same discussion applies here. An elliptic periodic point of period 4 could exist, and then I take L to the L squared time to escape the vicinity of it, right? So it's very interesting. It's very peculiar that this should even work at all, that this theorem should be true if on timescale so long I never accumulate a positive Lyapunov exponent, okay? Unfortunately, by the end of this talk, this will hopefully be not so mysterious. The answer is ergodicity. The answer is ergodicity. It's the same reason why the Poincare recurrence theorem is interesting philosophically, but practically useless, right? Recurrence takes longer than the age of the universe. For the same reason, right, after several universe lifetimes, I will exit the elliptic island, and then my statistics are a lot more favorable. Okay. That's roughly speaking why this works, or why it should work. But I want to get a little more into it. Okay, so this is I'll get back to this. I wanna talk about let me briefly mention some kind of related work in the volume preserving setting. So there's a paper by Ladrapier, Schub, Simo, and Wilkinson that studies random perturbations of twist maps on the sphere. Okay, so what they do is they take a very strong twist and then they rotate it by a random orthogonal transformation on the sphere. Okay, and if you take compositions of things like this, it actually has a qualitative similarity to the standard map, right? If you think of the standard map as a composition of a twist and a shear, right, then this is very similar to that recipe, but on the sphere, right? The random perturbations they take are very, very large. They're polynomial in L in the shearing parameter, though. So, and also the mechanism is very different. So this is kind of a separate thing. It's apples and oranges. There's also a very lengthy literature on kind of a la Furstenberg. So what that is, it's a set of very soft criteria that say that when the Lyapunov exponent is equal to zero for the random composition, that this implies some very strong degeneracy of the law of the composition of my diffeomorphisms, right? I don't want to get too far into it, but it's a very kind of soft thing, and it is, yes?
Sorry, can I ask you something about the previous theorem?
Yeah.
So,
Which theorem? I didn't want to talk about this yet.
no, not this one, even the one, yes.
Yes.
So maybe I missed something, but is this estimate sharp in some sense? I mean, what happens before these thresholds of, when epsilon is small, it reaches this?
I have no idea. I have no idea. I don't know. I'll tell you that L to the negative L L to the negative L is what we get in the proof. I don't really know if this result is sharp. It's hard to simulate in the regime where this theorem is valid. And I mean, honestly, Tom might have more insight than I do as to what capacity this epsilon threshold could be sharp. It might have to do with the length of time it takes to escape an elliptic island, or the influence of an elliptic island, right? It could have to do with a lot of things, but honestly, I can't really tell you sharpness, because again, that's entering deterministic land territory, and the deterministic problem I just can't do anything with. I'll keep in mind the fact that if you take epsilon to 0, if you manage to have a uniform Lyapunov exponent lower bound as you take epsilon to 0, then you could prove the standard map conjecture. And a route of this kind, not exactly this, but something similar to this, was attempted by Tom here and Leonard Carlson. I think that was in the mid-90s, right? Yeah. But unfortunately, that didn't pan out for that. What they were doing was different, though. So what they did, they had the deterministic standard map, right? And they did very intensive parameter exclusion on the L on the parameter to get rid of as many elliptic islands as possible. I don't know if you succeeded in getting rid of all of them, but no. But you worked really hard.
Very nice if you did, but no.
Yeah. They worked really hard to get rid of as many as they could. And then with what they could do, they started to look at the derivative process, right? So they started looking at directions of vectors. And they discovered as soon as you enter the vicinity of an elliptic island exactly this problem, that once you escape, you have no idea which direction you're pointing in. So what they did was they said, okay, well, maybe I'll add a random perturbation in the direction, right? In the tangent direction, and iterate that forward, right? And this worked in the sense that they got a positive Lyapunov exponent for this linear cocycle on the order of log L, or at least it was positive, right?
No, yeah.
It was on the order of log L, right?
And in fact, it would be a little bit better than that, because you get e to the minus L, speaking L squared, if you even with an elliptic island.
Right.
If you don't have an elliptic island, then of course you do even better.
Yeah.
I mean, if you don't have an elliptic periodic point of order 2 or 3.
Right. So you're saying not doing any parameter exclusion, but with a deterministic base and perturbing in tangent space.
You should be able to get e to the minus L squared.
Yeah. Okay. Well, whatever. I do what I can. Right. But then,
I think, in our case, we added the noise in a different way, as you said.
Yeah.
We added to the linearization, but I expect not too much difference.
And unfortunately, this didn't pan out for proof of the standard map conjecture, unfortunately. So I would like to talk a little bit about the proof, because the proof is kind of simple, and simple proofs are nice. And maybe it sheds some insight as to why random dynamics is simpler, fundamentally. And so, okay, great. So let's try to do that with the remaining time. So this is just a little summary of the system we have. Standard map with these kicks, these IID kicks in the x direction, right? And so the first observation is that this induces a Markov chain on the torus, right? It's a random process that only depends on the memory one time step behind. So Lebesgue measure is almost surely invariant under this dynamics, and so it's a stationary measure for this Markov chain, right? Now, this is kind of a funny thing, but what I want to say here, this line, is that morally speaking, you should think of, even though I'm kicking only in the x direction, so you might be worried that this is kind of a singular random perturbation. This is actually, morally speaking, an absolutely continuous random perturbation, right? Because if I compose two random maps, okay, it's the same thing as composing two deterministic maps on a randomly chosen point in an epsilon squared pillbox. So really, you should think of this as an absolutely continuous random perturbation. The reason we go for just this is, I'll get to that. I'll get to that a little bit later. But anyway, I just wanted to point that out, that this is morally speaking an absolutely continuous random perturbation. And so if you apply absolutely continuous random perturbations to a conservative system, to a volume-preserving dynamical system, the induced Markov chain is always ergodic, right? This is a matter of the phase space being connected, okay? You think of it. You can think of it like this. If you right, in the first time step, you start at a point. I'm on the torus. I start at a point. I smear in an epsilon pillbox, and then I map it forward. Okay? And because it's volume preserving, this pillbox might get a little funny. But when I map it forward, okay, it has the same volume, right? And so what you show is that now, all right, now I can smear again in an epsilon pillbox of each neighborhood, okay? And then map it forward again. Okay, and so what you basically show is that the support of, say, the second iterate of my Markov chain, right, has volume greater than or equal to something like 2 epsilon squared, something like that. Okay, something of this kind. Okay, This isn't actually true, but it's good enough for lie. Iterate this argument a few more times, okay? And then I ask the question, assume that I don't cover all of phase space with the support of xn for some n. If the support doesn't cover all of phase space yet, then there's some pocket that's avoided, say here. There's some small piece that's avoided, okay? And I take a little bite out of it with the epsilon pillbox. And so the volume of the complement, of the support is less than the volume of the complement from before. This is just the support as a random variable, right, on the torus, minus 1/4 epsilon squared, something like that, because I took a little bite out of it, okay? And you keep applying this argument. Eventually, you run out of volume, okay? So that's all a bunch of nonsense to say that Lebesgue measure is the unique stationary measure for this Markov chain, okay? So in Markov chain language, you say that the Markov chain is ergodic, right? This is kind of a bad terminology because in dynamics, you would call this uniquely ergodic. But I think that's a bad thing to say, too, because I don't really mean uniquely ergodic. I mean that the random system has a unique stationary measure. It's a different thing. Fine. OK. And now, by whatever abstract theory you want, Kolmogorov 0-1 law or multiplicative ergodic theorem, the top Lyapunov exponent exists and is a constant almost surely. And actually, based on very well-known theory, a very well-known theorem of Furstenberg, well, an elaboration of a very well-known technique of Furstenberg, you actually know that for any positive epsilon, this number is strictly positive. OK. I don't want to talk about that, but again, it's not so interesting because you don't know what that number is. And for all we know, that number is like epsilon itself, right? It's not meaningful, right? What I want is log L. What I want is to shake loose the hyperbolicity in the system, right? And to really see that coming from the dynamics. Yes?
So how much does, because I know nothing more about this, so because you put in this so-called random perturbation, how much does this depend on the actual underlying f and not just on the co-cycle level, but on the level of the derivatives? I guess it very much, I guess. But, how much does it depend on what properties of f? You say shake loose the hyperbolicity, so you're using there's some sort of.
We're getting there.
There's hyperbolicity there that is very difficult to detect without putting in this. But you'll get there.
Yeah, I'm getting there. I'm getting there. I haven't gotten to it yet. This is just basics. So the next step is, how am I actually going to do this? How am I going to estimate Lyapunov exponents from below? And the way I'm going to do it is by using stationary measures for this process, this Markov chain on the space of directions, okay, the projective bundle, all right? So xn is the same as before. It's just the Markov chain on phase space that is defined by this random composition, okay? But now I'm keeping track of this extra datum, this unit vector vn, okay? That is just the push forward of the unit vector from the previous iterate by the derivative, okay? And so this is a Markov chain on a compact set. It has stationary measures. A stationary measure for this chain projects to Lebesgue on the toral factor, right? So in fact, the Lyapunov exponent for Lebesgue measure, right, the Lyapunov exponent, is going to be bounded from below by this average with respect to any stationary measure for the xn vn. Actually, the stationary measure is unique, again, by kind of highfalutin theory that I don't really need. But irrespective of whether the stationary measure is unique, you always have this lower bound. OK? So I'm averaging this is the average derivative growth, right? And so this m hat is really telling me how frequently a tangent vector is pointed this way or that, okay? And so the game will be to check that m hat does not assign too much mass to the set of contracting directions, okay? To the set of directions that are oriented roughly parallel with the y-axis.
So can that be an equality? I mean, you expect that to
Oh,
be
it is
equal?
an equality.
Okay, so
It is an equality, but I don't care whether it is or not. This whole game is for bounding Lyapunov exponents from below, and this is unconditionally true. Okay? And so what I'm going to do is I'm going to play around with stationarity. Okay? I'm going to play around with stationarity. All right? And so I don't change this quantity. I don't change this quantity if I precompose by a few iterates of the random dynamics, okay? As long as I take an expectation at the end, this is totally kosher, okay?
So far you've used what properties of f? I mean, is this
Nothing. This is unconditionally true.
Okay.
This is unconditionally true. I'm sorry. I know I feel like I'm leading you by the nose and I haven't told you where I'm going, but I just want to, yeah. I'm sorry. Maybe I didn't organize this very well, but this is whatever this f hat is. It's how this random map maps points and vectors. Okay. So here I'm finally going to start using the dynamics. Okay. What I want to prove is that for most points x, for x in this good set that avoids the critical line until time n, the mass assigned to the set of x naught v naught, for which vn at time n is an angle greater than pi fourths, okay, is really, really small. All right. So here, I feel like I should really draw a picture.
So here, this critical line is this critical set you're talking about in more general.
Yes. Yes. Exactly. Exactly. So, so think about the unit circle, right? What this is saying is that if I look at m hat, say, disintegrated over points in the torus, so each one of these is a measure on the projective line, or the projective circle, okay? Then the mass here inclined in the vertical direction, where I can see contraction, okay, is extremely small. So statistically speaking, most vectors, most of the time, vectors are oriented in this direction, okay? And so when I look back at that average formula, okay, most of the time, the m hat is sampling a vector which is at an angle at most 45 degrees to the positive x-axis, okay? And since most x's are away from the critical line, I'm typically sampling a number here that is on the order of log L, okay? And so this is what I'm aiming at, okay? Unfortunately, the way I just said it and the way I formulated it here are slightly different. But let me attempt to bridge the gap. So I don't actually directly prove an estimate on m hat, but you agree that if I could estimate the mass of this cone, right, in the projective bundle, if I could estimate the mass of this cone, and I could show that it's really small for very large L, then I would conclude a large positive exponent. Okay? I don't exactly do that. What I do is I play a stationarity trick, okay? And I don't even bother averaging in the omegas, okay? I don't even bother averaging in the omegas. All I do is I take this m hat, I push it forward by these fixed random maps, okay? And then I'm going to evaluate at the last step a single iterate of volume growth or decay, okay? That's what I'm going to do, all right? So think of omega 1, omega 2 up to omega n plus 1 as fixed, arbitrary samples, all right? Then, okay, think of it like this. Okay, hold on. All right, so with omega 1 up to omega n plus 1 fixed, right? Lebesgue measure is invariant, right? So the set of points that avoid the critical line, if the critical line has, if you think of it as being fattened by a neighborhood of 1 over root L, right? Then the set of points that ever even see the critical set is less than or equal to n 1 over root L for any n, right? Obviously, if I take n to infinity, this blows up in my face. But if I fix my n, right? If I fix n to be on the order of root L, or the fourth power of L, okay, then most points avoid the critical set, okay? So I'm completely ignoring all elliptic islands. I'm just dropping them. I'm throwing them out, okay? Then I'm left with estimating the m hat concentration of the set of base points that are doing this good thing and avoiding the critical line, but for which the vectors at time n screw up, okay, and are pointed in the vertical direction, okay. So if I can show that the m hat of this set is small, all right, then what will I have? This piece here will have two contributions. There will be an integral over the set of points that failed, right, the Bn, plus the set of points that stayed away from the critical set, like good children, right? And so I subdivide this again into two pieces. The first piece where the angle of Vn with the x hat direction is small, and the angle with the x hat direction is large, okay? This is going to be a contribution on the order of n L to the negative half, right? This is going to be end. This contribution is going to be the thing that gives me my log L, okay? Greater than a half log L, let's say, times whatever the m hat mass of this set is. And this, by this main lemma, is supposed to be made really small, okay? So that's where this estimate is coming from. Now, Barney keeps asking, where the heck did the dynamics go? We can finally talk about dynamics in the last 5 minutes of the talk. This was horribly structured, and I apologize for that, but that's life. So you might be wondering, why did I iterate n times to begin with? Okay? And this is the reason, all right? Is that based on just completely general things, right? Based on the fact that I smeared absolutely continuously at every time step, okay? The stationary measure for m hat cannot be too concentrated. To start with, cannot be too concentrated in the vertical direction, okay? So whatever I start with here before I push it forward is not too concentrated in the vertical direction, okay? And every time I apply one of these f hats, well, it was an f hat drawn where x is in the good region. So it's a matrix. I'm applying a matrix that looks like this, okay? And so whatever mass there is in the vertical direction, okay, is dragged away, is pulled away, like stretched out, okay, right? Because contracting directions are sources in the projective, right? In the projective action, they're sources, okay? And so the hyperbolicity is taking mass away from the vertical direction and kind of tearing it away from the vertical direction and feeding it to the horizontal direction, okay? And so that's why so little mass will actually remain at the end. All right. So that's what I say by pushing mass away from the vertical cone. It's just shearing that mass away from the cone, okay, shedding it. So I want to take n large to shed as much mass as I can, but I can't take n too large because then the set of bad x's is too big. So you do a little balancing act and optimize, okay? So you optimize where this is like on the order of like L to some small negative power, right? And then whatever n I can get away with is where I pin my epsilon, okay? And so I calibrate my epsilon to be just barely large enough to make this number order 1. So as you can see from this example, I can take epsilon to be greater than L to the negative 1/6 n, right? N is some power of L, and that's why I can get such a small epsilon. Okay, is precisely for this reason, because Lebesgue is invariant. Okay, so I can shed a whole lot of Lebesgue mass. Okay. And then take that time to shed mass from the vertical direction. And when you combine these two things, this is what you get. And actually, this argument worked for every omega 1, omega 2 up to omega n plus 1. Okay? I didn't even have to average in them, right? I was effectively using the noise, though, because I was using some non-degeneracy of the stationary measure. Okay, I needed to use that the stationary measure had a density to begin with, something that I could control actually, and then I could begin shearing that mass away. If there were just some atoms sitting in the vertical direction, right, that just got stuck there, I can't conclude that I knock that atom out. All right, so this argument doesn't work, for example, for discrete random perturbations. Right? You really need something absolutely continuous here. All right. Well, that was a technical slog. So I think I'm going to skip to the conclusion. All right. Thanks for sitting through this. My parting words, right? If you didn't get anything out of this talk, my parting words are this. Okay. In contrast with the situation for deterministic dynamics, for random dynamical systems, you should be able to estimate the Lyapunov exponents. You really should, okay? And you should be able to estimate Lyapunov exponents in such a way that you can actually estimate them on a computer, okay? The best possible results you should expect in the deterministic setting are there exist parameters, right? Or there's a positive Lebesgue measure set of parameters, blah, 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 right? But for random systems, you should be able to know what those parameters are, okay? The kinds of considerations I made just now to do these things didn't depend on the fine structure of L, didn't depend on carefully calibrating things. No. I dropped enough of the Lebesgue mass, right, so that I could get away with this trick with epsilon sufficiently small. Right? This is not a game. Okay, maybe I'll stop there. But not only that, but this method should be executable for high dimensional systems, right? It's really just a matter of understanding the bulk hyperbolic geometry going on, right? is this system hyperbolic on 90% of phase space, and how bad is the twisting in the remaining 10%? Considerations like this. And then, of course, my parting words, that the real world is inherently noisy. There's really nothing wrong with adding noise to these systems. If anything, it's almost better to add noise from some perspectives in this game. All right. Well, thank you very much. I think I'm done. Thanks.